Let's see, which side do I want? Let's do that side. Let's do over here. All right, so we're about to get into chapter 8. Believe it or not, this is kind of, chapter 8 is our first steps into analyzing claims. So a huge part of statistics, and I'm pretty sure you guys know this, is analyzing a claim somebody makes. So whenever you hear a commercial and they say this has been clinically proven to blah, 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 right? Clinically proven means good evidence was found. You can't really prove something like that. You can just find good evidence for it. So we're going to start to talk about all the stuff we've been doing so far this semester. How does it go into analyzing a claim somebody makes? Right? So, for example, I could set up, I think I might have used this example before. I could set up, yeah, I did, I'm pretty sure, a class, like I can offer a workshop that's supposed to improve your SAT score, right?
Yeah.
And I have to do some statistical analysis to be able to say it's been clinically proven to increase your SAT score by 20 points. And at the bottom of the screen would say the deviation in your expected results. That's where I put some of the more weird stuff at the bottom, just as a disclaimer, right? Everybody with me?
Yeah.
So the thing about whenever you hear that it's been proven that you'll lose 20 pounds or you'll gain 20 points or whatever, that's an average. So you could be somewhere outside of that standard deviation wise, right? So maybe you get 2 points, or maybe you lose 10 points, or maybe you get 50 points, but 20 is kind of like the average. You guys kind of with me? Okay. So, chapter 7 kind of can be seen in a few different ways. Let's see, how do I want to start this off? So if I have, let's say that, let's say that we know the standard deviation for, oh God, okay, let's go with that, Jeff. So weird up here sometimes. The standard deviation for all fertile shell thickness is 0.92 centimeters. Okay, that's, whoa, all right, I'm sorry. It's just known. All right, so one thing I want you to understand, I don't know if anybody's noticed, has anybody looked ahead on the homework sheet? Has anyone noticed something weird about chapter 8? And you're all like, what? Look ahead? Are you insane? So if you look ahead, it says 8.1, 8.3, 8.2. So I do chapter 8 out of order. 8.2 is going to be where we don't know this, because that's probably more true to life. If I go, has anybody ever seen the movie Arachnophobia? All right, so it's all about these people, they find a new species of spider out in this remote area. So if we go to an island and we find a brand new species of something, do we know anything about it? We just found it. We're looking at it, we're like, are you gonna eat my face? No, okay, right? So I'm gonna be back here going, yeah, tell me how it goes. So we just found this thing, we don't know anything about it. So we shouldn't know the population mean weight of these things or the standard deviation of whatever. But this kind of problem, we've already got a lot of data on these certain kind of turtles. So it's kind of assumed, it's kind of known that the standard deviation is this. Everybody with me?
Okay.
We go to a remote area, right? Sounds like the beginning of a horror movie. And we find, we take a sample of, let's say 43 turtles, and find a sample mean of, I don't know what makes sense for us.
87.
No, 87 centimeters. That's a thick ass turtle. Okay.
Wait.
1 point.
Oh, I'm sorry. Point.
Let's say
whatever.
2.03 centimeters. All right.
Okay, I'm
So
sorry.
we're talking about shell thickness on a turtle.
I meant point.
Don't worry. Don't worry.
It's the world's largest.
I should just clear that up.
Like they're just giant.
It's like this tiny little turtle in this monster shell, right? Okay.
Really sorry about that.
No worries. I love it. We all need some levity in math class, for damn sure. Okay. So, what I want to do, this isn't really good enough. I mean, what's the real mean? Do you think this is all the turtles that are in this area? Let's say this is kind of a big area right on the coast of something, I don't know. Right, so there's probably a lot more turtles than this. Are you with me?
Yes.
So this is just a sample. So what do you think, what do we think about, what do we know about mu? What would this be in this case? I mean, don't give me a number, because if you do, that'll freak me out, because you can't possibly know it. We don't have a freaking clue what the number is, but what does it mean?
The mean.
The mean of?
Population.
The population. So this is the sample mean that we can actually get. But what I really want to know is what's the sample mean. So let's say, a little backstory, we're concerned that there's chemicals coming from some factory that could be causing the turtle shells to not grow enough. Like they're not as thick as they're supposed to be, which would obviously put them in danger, because that's why their shells exist. Are you guys kind of with me? That would be bad. I have no idea. Some days I have no good example, and some days I'm like, stupid detailed example comes out of nowhere. Turtle shell thickness, why not? So what do we know about mu? Well, can you guys tell me anything? What do you think, what do we know? Do we know anything about it?
About mu?
Yes.
Yeah.
What's the only thing that we know?
It's the mean of a population.
All right. What do we know? What did we look at? We looked at how many turtles?
43.
And what did we find?
This-
We know their sample mean thickness is this, yes?
Yeah.
All right. So shouldn't this be kind of close to this?
Yes.
Okay. If we took a really good sample, I would expect it to be. Does it have to be? No, but I would expect it to be. You guys kind of with me? Yeah, like it. If we randomly selected 43 gross month students from every gross month student, we found their average age, I would think that would probably be kind of close to the real average age, right? If my sample was really good, well picked, random. Okay, now. So one level of how you look at what we're going to do in this chapter is improving on this. Instead of just giving us a number, we're going to create a range around that number that communicates our uncertainty in it. Okay, all right, I like it. So we're going to do a little sidestep here. We're going to leave this problem for just a minute. We're going to come back to it. Now that I've sort of set up a problem, I want everybody to understand what the thing is. And I'll tell you one more thing. So this is the mu for turtles in that area. Yes? You guys with me?
Okay.
And let's say that we know that the mean for, no, I'm going to tell you that later. Ha. Okay. It's a little side notes. Okay. So let's figure out what we need to do to sort of improve on this guesstimate. So any sample mean we take is basically a guesstimate I'm not the biggest fan of that word, but you understand what I mean when I say it, of the actual average for all the turtles in this group. Right? That's our best guess, is this. So, let's assume for a second that that is the real mean. Let's assume that 2.03 is the real mean, just for a second. How do I, and by the way, I've drawn a normal curve. Why did I do that? How could I do that? Do we know that the turtle shell thickness is normally distributed?
It's over 30,
Ah.
so it's close enough.
Yeah, so this is a picture of all the groups of size 43. I like it. Right, n's greater than 30. You know it's normal enough. How far would I have to go to catch 95%?
2 standard deviations.
Be more specific. 2 is good enough to remember real quick for empirical rule. We now have the z-score chart where we can find the exact number. So it's going to be close to 2.
Hold on.
So what z-scores do we need to find? Don't I need to find this z-score? And that z-score, yes?
Yep.
Okay, now. The chart only understands areas below a z-score that I want. I want this z-score, don't I? What's the area below that z-score?
5. 0.5.
Yeah, 0.25, right? 2.5%. There's 5% outside, so there's 2.5%. Can you guys look that up? Maddie, just a second. Sorry. Everybody, can you look that up and see? You already know it should be close to like -2. So get as close as you can to 0.025 in the body, right? That's where the percentages are. Yeah. -1.96. Can you guys see that on the chart? And I think is it exactly 0.25? I think that's one of the ones that are exactly. And then what's this one got to be then? We've done this kind of thing before. Yeah, this one's got to be positive 196. I like it. All right, kick ass. So, we've done this work before. I've been getting you ready for this chapter for a while. So I want to figure out, we've got one group of 43 turtles. I want to kind of know 95% of the time, where should groups of 43 turtles be? Within what range, within what interval? So that's what I'm going to try to do. I'm going to try to make this, can you make this into a turtle shell thickness? Do we know, you can do it, Jeff. Do you know sigma? Yes. Why am I using this one? Because that's true for all frickin' turtles. So is it true for my turtles here? Yes. Okay. What do I have to do with this though?
Multiply it. No.
Where did we? Yes, divided by square root of 43, because that's the one for individual turtles. I need the one for groups of 43 turtles. So I got to change it into this dude. Uh, 0.142. Make it shit up. I don't know.
0.14.
What is it?
0.14.
0.140? 140? Okay. Oh, neat. That was pretty good for me. So then I can figure out, so I really want you to understand, this is the sample mean we found. if I go down this many steps, I'll get to that range. I'm sort of doing, it's kind of related to the max and min usual values, right? It's not quite that, but it basically is very much related to that. So what am I going to do then? I'm going to take, okay, I'm basically doing this. What are you doing over here? So I'm going to take this minus 1.96. Doesn't this make sense? Don't I want to start here and I want to go down 1.96 of these?
Okay.
And then I'm going to do the same thing, but I'm going to go up 1.96. All right, so I can actually write it like this, couldn't I? Ooh. Can somebody figure out what this piece is by itself first? Because that's sort of like, it kind of makes sense. 2.03, give or take what? .2744. That makes sense. And now you can just subtract that and add that to this dude here. Get a little interval. I guess 1.756, is that right?
Yep.
Up to 2.3044. Don't worry, I'm going to come back in, we're going to discuss further.
Do you want 3 or 4 decimal places?
Well, to be honest, one thing is, you basically always go one more place than this, so we could have just stopped here, but more is fine. So the general rule is whatever this is, you go one more place than it.
Okay.
Yeah. For this. Can you guys see why we might call this, so this is what we got from our sample, correct?
Yeah.
And you all agree with me that the sample mean is more than likely not the population. So there's some kind of, not mistake in it, because we don't make a mistake. We didn't make a mistake, it's just off by some amount. And if I'm off by some amount, couldn't that be called an error? So it's not like we made a mistake, but we just call this the error part. Because it's what, give or take this. It's how much off from this that the real mean might be. So it's a lot more information to tell somebody that this is the interval for the for the weights, for the thickness, instead of just telling them one number. We give them this range. Now, let's see, which order do I want to do things in? Now I'll tell you this. What if the average for all turtles, the average cell thickness for all turtles, you all, was 2.11. No, Jeff, try again, buddy. 2.41 centimeters.
So.
Look at our results. What does that mean about our turtles? What is that evidence of? Yeah, look at our turtles. It looks like our turtles would go up to about this much, right? For thickness. So what this is doing is it's taking the fact that this is just a sample mean. It's kind of building in some error, so that this is a better kind of estimate for what the real mean is. Instead of just giving one number, I give a range. If the average for all turtles was this thick, our poor little turtles look like they're almost definitely not that thick. So there's evidence that these turtles in this area don't have the same shell thickness.
So what does that mean that we did?
Then I want to go in and do some further testing. Then I might get some chemists. So at this point, I've done nothing but math. Now I can get some people to come in. Now maybe I can get some funding to get some chemists to come in and check the water and whatever. You guys kind of with me?
Yeah.
see if there's anything, get some biologists who can come in and say theoretically what would happen if these turtles were exposed to this chemical at too high of an amount, what would happen? Oh, the shell thickness. Oh shit! And then put together a big thing, guys, right? And then get them to do better with whatever they're doing with this factory. Okay. Yes?
Is it always the 95% counting the?
No, that's the next thing I'm gonna do. I love it.
Okay.
That's perfect. That's perfect. That's what I was just thinking about. What did I want to do first? All right, so that kind of wraps this up a little bit. Now I know this is the first time we've done something, but there's a lot of shit to this that's very familiar. So Audrey is pointing out that did it have to be 95%? No. How much data did we catch if we do this? That's kind of a silly question.
95.
95% of the data. How sure are we then that we caught a specific data point?
95.
We're 95% confident, right? What if I go out, there's a certain fish I want in a lake. There's a certain fish, it's this damn fish. I've been trying to get it since I was 7. Just damn fish. I don't even like to fish, by the way. But there's damn fish. So I go out, I'm like, I'm gonna catch you. And let's say I get a net big enough to catch 95% of the fish in this lake. Right? Not only are the townsfolk angry at me as they're coming up around the corner wanting to go fishing, you know, what's the probability that I caught that damn fish?
95.
95% chance, because I caught 95% of the fish. I haul it up and there he is still in the lake. Damn it. I'm sorry. Okay, that was a whole side thing. I'm sorry. So I really want this to make sense. The problem is going to tell you how confident you want to be. So if this would be a 95% confidence interval. Now you see where all those words came from. Because I'm 95% confident in this interval. So let me talk a little bit about, this is kind of backwards from what I normally do. This was very specific. Now I'm going to talk about concept, right? Yes?
But real quick, if it was like a homework problem, what would a homework problem look like? If it was like
This. Believe it or not.
But you said it would show you the.
Yeah, it would say create the so this would have said create the 95% confidence interval for the shell thickness of turtles in this area. Yeah, and this would have been the answer. That's the interval that's 95% confidence because we found the z-scores from that 95%. Okay, now. There was a huge assumption that I made that I'm surprised nobody's yelled at me about. How could I put that in the middle?
Say it again?
How could I put 2.03 in the middle?
Because you said let's assume this is. the
Ah,
answer.
see, that's a huge assumption, right? Okay, so let's talk about that a little bit. And the results here. So here is the reality. When we came on this, when we found this little area, we got worried about the turtles. Did we know what the average shell thickness of those turtles was?
No.
No. Do you agree that an average shell thickness exists for those
Yeah.
turtles? Yes, of course. It's not like you can go pick it up, but there is an average shell thickness. And if we were able to catch all the turtles, we could figure out what it was. So let me see if you guys really get what I'm. So there is the average cell thickness. There it is. We don't know what it is. We take a sample. Now, I just put it there just for reference, but it could have been anywhere. It could even be equal to this, but more than likely not. Yes? More than likely it's going to be off somehow. Can we stop for a minute? Okay, now, when we construct that interval, that's what it would look like, possibly. And here's the complete idea. What if another group came and did their own study and they calculated a mean? Does it have to be here?
No.
No. Couldn't it be here maybe?
Yeah.
Right? They just happened to pick a bunch of turtles that were that over there. And then when they make their interval, maybe it's this. Did they catch the real mean? Did we catch the real mean? Look at the picture.
Well, we did, but
We
they-
did. If this was the situation, and understandably, this is all made up, I understand. I didn't actually go look at any translation, but if this is the situation, did one of us catch this? Yes. Did both of us do all the same work? Yes. I'm going to say nobody made any mistakes. We all did exactly the same work. So what 95% really means, it isn't that this is in the middle, to be honest. What it means is, if 100 people, and I don't have 100 colors, but if 100 people came in and did their own intervals, got their own means, made their own intervals, 95 of them would catch the real mean on average. So 95% of the time, if we follow the process for confidence intervals, it will capture the actual mean. So there's a 5% chance we're wrong. Let me stop for a minute. So what if I want to be 99% confident? What would change?
Your area on the Z-score. chart.
Yeah, because I'm going to want to catch more data, right?
Yeah.
So then each of these would get wider, and we would probably all catch the real mean. What would it take to be 100% confident?
You can't.
No, you can.
You can, but you have to go to 3.5.
No, you have to go from
Okay.
negative infinity to infinity, but I'm not going to put that in there. We think that the turtle shell thickness is somewhere between negative infinity in centimeters to infinity centimeters. Then I'm 100% correct. Yes?
They're gonna give you any money.
No, they're probably not going to, not only just not give me money, but they're probably going to block my number and everything. Okay. I don't know if you guys are really with me. This is what's so cool. I know you probably don't agree with me yet. But we are going to do like something, probably not today, but definitely not today because they didn't bring it with me. Where have everybody kind of create their own confidence interval from a certain set of data, and then we actually see, did that percentage get the real mean? I'm not going to tell you what the real mean is ahead of time. Anyways, that's in our future. Sounds exciting.
Oh, so is the confidence interval always going to be told to us?
The level, yeah, the confidence, the percentage.
Yeah.
Yeah, they have to give it to us. Now, every time I teach this class, I always forget to say this, and this has shown up already in the book. So help me out. 95% in there. What's the total percent that's outside?
5.
This, can anybody tell me if you've seen this? So that's 0.05, right? That's the 5% that's outside. This is given the symbol alpha. Have you guys seen that symbol yet in the book? Alpha? Okay, not yet. Okay. You have?
Wait, 0.05 specifically is
No,
that?
no, no,
or
no,
it's
no.
just about outside?
Yeah, alpha is the
Okay.
area, so let me make this, in this case, it would be 0.05. What would it be in this case?
0.01.
0.1, I like it. So what's alpha over 2 in this case up here?
0.025.
Isn't that the one we looked up? Because that's the area that's down here.
Yes.
So alpha, the symbol alpha, is the area and the tails. So if you see that symbol, so if I told you, I don't think the book is going to say it like this, but I know they sneak this symbol in sometimes. But if I did say create a confidence interval using alpha equal to 0.02, what confidence level would that be?
98.
98%, right? Because the alpha is the area outside. Does that make sense? So it's just yet another Greek letter. Statisticians sat around, they're like, what Greek letter have alpha? Oh, alpha's the first one. Shit, we better use that thing. So you can tell why they used alpha, because alpha is A, and A for area. Ooh, we're creative. All right, now. Going even deeper. Okay. Here we go. I can erase this. I can erase this. This has been up here for a while. Go ahead. go even more technically conceptual here in a second. Hold on, here it comes. Does this formula look familiar to anybody? Right? Yes. And what we just did was kind of related to finding these z-scores. And I think I've written it like this before, like this. No? Remember when we said bounding the middle something percent? I might not have, I guess maybe I didn't, but sometimes I like to sneak that in just to get us used to it. Plus or minus, because I gotta go up and down, correct? Just like we did a minute ago. And then what's gonna happen to this? Oh, two things. All right, let's do that first. Do I know this in these problems for whatever I'm analyzing? No. I don't know what it was for those turtles. That's why I took a sample, right? So I can't use this, can I? I have to use this. So that's why we use 2.03, and that's why I pretended to put it in the middle for a minute. So if I don't know mu, the next best thing is sample mean. Give or take. Now, if I take a sample mean, I must have taken a sample. So what's got to happen to this? The same thing we just did a minute ago. What's got to happen to the standard deviation? Divided by?
The n.
Square root of n. This is the formula that we just used, correct? 2.03 was our sample mean. Give or take 1.96 was the z-score. I don't frickin' remember what this was. 0.92?
Yep.
43?
Yep.
It's almost like I'm good with numbers sometimes. Right? We did this. You guys didn't question it because it was shit we had done before. So we've never written the formula anything like this before, but it just catches the stuff that we would do because it's the right thing to do. So that is the formula for a confidence interval, for a mean. Okay, now. So let me ask you a couple of, let's see if you guys can do this. Everybody got their z-score charts at the ready?
Okay.
Can you guys find for me, what would the z-scores be if I want to be 99% confident?
.50. Or wait. You want 99 flat, like 9900? Or 9999?
Draw the picture.
Oh, okay.
If you don't draw the picture, you will do it wrong. What's alpha? That will help you out. Let me ask you this weird question. Can everybody draw the picture? And how do you put the confidence interval in there? What do? You chop, right? Right? Chop. Yes? Can I ask you a weird question? How many tails did I just make?
2.
One on each side, right? So there's 2 tails. So this is 99%. How do I find the z-score? Well, I need to know the area that's here. I need to know alpha over 2. This is where this is going to sneak in. What's the area in this tail? What's the area outside?
0.01.
1, 0, 1. Yeah, 1% outside because there's 99% inside. So then what's on this side?
So
0, 0, 5. So what, anybody get that z-score yet? 0, 0, 5 area?
negative 2.6.
Doesn't it have a-
Negative 2.575.
There it is.
Yes.
Remember, for 95% it was 1.96. Why does this make sense that it's bigger? Because I got to go further out to catch 4% more data. Does that make sense? So if I only wanted to be 80% confident, the z-score is going to get much smaller. I don't have to go anywhere near as far out to get 80%. You don't see a lot of 80% confidence intervals. Those kind of suck pretty bad. The standard, the most often used one is 95%. Okay, so let me keep this up here. Let me give you this. In keeping with the aquatic animal, although I know turtles are amphibians, but still, I got a problem here about dolphins. Try to do. See if I can get that all the way around. Oh yeah, that back there too. Yeah. I'll get it. I think. Yeah. Oh yeah, that's right. Forgot about the best part. Try to do what you can with that first problem. So this one, there's not much work to do for the z-score, right? Because we already know what that is. Right?
Yes.
So I really wanted, I don't know how this is going to sound to you guys, but does it make sense that the formula has plus or minus in it? No? Of course it does, right? Because we have to build our interval by going up so much and down so much. So that's why they give or take. So when you find the z-score, don't put negative. It's already built in. The negative is already built in. You just care about the number. So don't mess yourself up. People put the negative in there and they're like, what's plus or minus a negative? No, it's already in there. You know, it doesn't matter. Okay. So now it's just a plug and chug situation. All right. Keep going. We'll do the conclusion together because we haven't talked about that yet. This will be everybody's favorite part. most of your problems. The only thing you're not gonna be told directly is what the z-score is. So if we do this, I highly recommend you do the error part first. Bam! Is that what you guys got? 1.324. So this goes 92.6, so I just have to take this out to 1.32. So I go on one more decimal place than the mean. And let me, this is not that big of a deal, but let me just show you a little neat thing you can do. I can store, see the little stow button? I can stow that in my little X button. Bam! Zoom in on you. So I store that in X, and then I can just go 92.6 minus X, 92.6 plus X. Is that what you guys got?
Yeah.
Okay. So my interval is 91.28. Rounding that off to 93.92. See again? This here? Oh, okay. Bam, bam. Bam, bam. We didn't need to, right? Because we already did like the 95% confidence interval before. So we already knew this 1.96. But if I told you like 96% confidence, you don't know that much. You're gonna draw it, 4%, 2%, look it up. I like it. Now, what if I told you, so the conclusion is something you're gonna have to do. If you don't do it, the problem's not done, you lose points. Oh shit. Conclusion is a big old sentence you gotta write. But real quick, what if I told you that the average length of dolphins is known to be 93.17 inches long? Do these dolphins look to be different?
Not really,
Why not?
because that falls within our.
Yeah, it's within here, right? If the average length of dolphins was 95 inches, then this would be evidence that these dolphins, wherever I am, seem to be malnourished or something, right? They're shorter than expected. Does that really mean there's a problem? No. But it means there's something to look into. Maybe there is a problem, we don't know yet. Maybe they just happen to be shorter in this little area, we don't know. Maybe. So how does this work down here? Here's the conclusion. We are farmers, no stop. We are, how confident are we about what we've done?
95%.
Yes, which is pretty good for me. I don't know about you guys. We are 95% confident. And I really want you to remember this picture I drew that's now gone, damn it. Yes, where there's a mean, before we even come to this area, isn't there a mean dolphin length of dolphins in this area? Before we even get there, there it is, it's just sitting there.
Yeah.
While the dolphins swim around, then we get there and we take a sample and we try to catch this. And our sample is our hope, right? So when you put this down, this is important. This isn't just semantics. We are 95% confident that the interval we created, now careful, don't start writing it. Just listen to me for a second. That the interval we created catches the real mean. Okay, let's listen. So we are 95% confident that the interval 91.28 what?
Dot, dot, dot.
No. 91.28 inches to 93.92 inches contains the true, let me see. Let me get away from saying true. Contains the population mean length of dolphins in this area. Aren't you excited? That's going to be part of every single problem you do. Yes, John. So don't say we're 95% confident that the mean length is inside our interval. That is actually not, I'm not just being picky, although I am a math teacher, it's part of the whole thing. But it's just flat out wrong conceptually. All right, now I want you to do part B. Can you just answer the first part? Just tell me, would the 90% interval be smaller or larger than the 95%?
Smaller,
Why?
because it's less than 95.
To be 95% confident, how much data do I have to catch?
95%.
95% of the data. To be 90% confident, I have to catch less data. So I really want to make sense why that's going to be a smaller interval. So go ahead and try to calculate this. The only thing that's going to change, yeah, it's the same problem. Everything's the same except we're not doing a 95, we're doing a 90. Yeah.
So we're 95% confident because the 92.6 lies between those intervals, correct?
No.
And how-
We're 95% confident because that is what our z-score did for us. It caught 95% of the data. What we're going to do here is going to make us be 90% confident because we're going to find the z-score that catches 90% of the data. And real quick, don't, this is nothing about you specifically because I see this all the time. This, by construction, will always be in this, yes? Because it is the middle. So it being in there doesn't mean anything, because it's what we created the thing off of. Okay. I always get somebody get kind of mixed up about that.
So, first one. Is first,
Oh, yeah. How far off was it? Oh, it was quite a bit off. What happened? Yeah, that would have done it though.
I did this first.
1.96 times 1.32, that's the same one we got just about.
I was checking.
But no, 92 points, so if you do 92.6 minus 1.3246, you don't get 90.68, that's what I'm saying, yeah.
So I just.
No, yeah, you get that, which is, I wouldn't have a, say,
So for here, I just.
yeah, so one reason that we actually build this into the equation is because of what you just said. So we actually don't round this at all. So, but what you did is fine. If something went wrong, because you shouldn't get 90, it shouldn't be that far wrong. It should be pretty close to that. And that actually is, yeah. So I mean, the formula is gonna be exactly the same. Have you guys found the 90% confidence? Yeah, if it's 90% confidence, what's alpha over 2? If it's 90% confidence, what's alpha over 2?
0.05.
Yes, 10% outside, 5% on one side. So what you guys, anybody who got the, this should look familiar, I think. Anybody get that z-score yet?
Yeah.
Yeah. 1.645. So everything's gonna look exactly the same, except we just don't have to go out as far, because we don't have to catch as much data. That's the only difference. So now the error is gonna be a little less than it was before. So did anybody get the error?
It was 91.49 inches to 90.
No, just the error.
Oh.
Yeah, 1.111, yeah. There's a few ones and then some stuff. say give or take. That's exactly what we're doing. And do you see how that interval lives inside of this interval? Does that make sense what I'm saying? That interval lives inside of this interval, yes? So this interval is smaller, which is supposed to be, because it's supposed to catch 5% less than the data. So we would say, what would we say here? We are
90% confident. You want me to keep going?
that the interval 91.49 inches to 93.71 inches contains the population mean length of dolphins in this area, blah, blah. Okay. Are you allowed to go blah, blah, blah? No, too bad for you. I'm the teacher though, do that shit. Okay. Now, look at your z-score charts, everybody. Look at the positive side. Always look on the positive. Okay. Look at the lower right-hand corner. Do you see anything related to what we're doing?
Confidence level, critical values.
What the shit? What does it say for 0.90?
1.64.
Isn't that exactly what
Yes.
So, what will Jeff do? Will Jeff always give you one of those three? No, because Jeff is an asshole. He's going to ask you to make the 97% confidence interval. Nah. But those three, 95 is the most, and 90, 99 are the next kind of most often used. You guys with me? I think the book uses 95 like a stupid amount, but oh well. I'm going to use whatever I want. Okay. Shoot. Now, before we do this last thing, good luck, man. Are you going to go all the way? No. Okay. Okay, I moved the camera over and I saw my eraser in my camera and I thought, holy shit, what is that? Okay. God, that was freaky. That is a big cockroach. No, okay. So do you start to get the idea of what I was saying? When you create a confidence interval, on one hand, it's just an improvement over giving somebody one number, the mean, right? It incorporates the standard deviation. It kind of gives a better idea. So like if team A went and got an interval from 80 to 90, and team B got an interval from, and this is a 95% confidence interval, got an interval from 85 to 87, which team is more certain about what they've done? Which team's numbers seem to be more...
Team A. Team B.
Well, if I ask my doctor, hey, what chances do I have? And he says, somewhere between 10% and 90% chance. Well, would you rather the doc say something more specific? Even if it was like 50 to 60, I have a better, than 10 to 90 is like, what are you doing? What? Where did you study? All right. So this team, for some reason, maybe they got a much larger sample, yes? If I increase my sample size, isn't that going to decrease my new standard deviation? It's going to make the interval smaller, yes? So that's the most immediate way that somebody could be more certain about what they find is they just take a freaking bigger sample, right? Okay,
Well,
so.
and isn't it that the bigger sample that you take, the closer you get to the population?
Of course, that's why the bigger my sample, the less error I need to apply because I'm getting closer to what the real population mean is. I love it. Okay, so here's the real thing I came up here to talk about. What part of this equation was the error again?
C times.
Yeah, this part.
Yeah.
So let's call that E.
Okay.
Okay. Right, because that's the error. We'll call it E. So what we're about to do let me see if this makes sense to you. What if I do a whole study and I get an error of 5 centimeters, right? And let's say that we're like, oh shit, I gotta know better than that. I gotta get that error down. What's the most immediate thing we just talked about that I could do? How can I get the error to get smaller? I can take a bigger sample. Wouldn't I like to know ahead of time how much bigger the sample needs to be? Right, what if I'm like, okay, I got 5 centimeters, I want it to be 2 centimeters. I'd like to be able to calculate something that tells me how big of a sample I need. If I need to look at 1 billion turtles, I'm gonna let go of that dream, right? I'm gonna say, no, I don't even know if there's a billion turtles anywhere in the whole world, I don't know. So what we're gonna do here is, if I know what my target error is, I wanna be able to solve for n. I want to know how big of a sample do I need to take. So how the shit, this is the little bit of algebra that sneaks in. How do I solve that for n? I want to solve that equation for n. What sucks about where n is?
It's on the bottom.
Yeah, so how do you immediately remedy that?
Put it on the top.
And how do I do that legally?
You gotta multiply it.
Yeah, multiply both sides by n, right? Because then it cancels here. Yes? Yes? Shake some dust off of that, some rusted dust or whatever the shit. Shake it off of those algebra brain molecules. Wow, Jeff. I should become a politician just based on what I just said. That sounded like no science at all. All right, square root of n times e equals z sigma. Is everybody cool with that so far?
Okay.
Now, what do I not want over here? E, so let's get rid of E. And then of course the last thing I need to get rid of,
The square root of that.
and how do I kill a square root?
Get a square root.
What do you do with a problem like the square root? Yeah, it's square, kills the square root. And that gets us to the last thing on this sheet. You guys see that leads us to here. You guys agree with me?
Yeah.
If you square all that stuff, don't you get that?
So,
So,
but now what is E?
don't worry. First thing I want you to realize is I've gone back to 95%, right? So how many dolphins gave me an error of 1.32? 37 dolphins gave me an error of 1.32, yes?
Yeah.
So now I need my error to get down to 1/2 inch. So I've got to increase my sample size. So the question is, it's definitely going to be bigger than 37, yes?
Yeah.
Okay. So didn't I just give it away? What is my error? What do I need my error to be?
What? 1/2 inch.
Yeah. It's 95% confidence, so I'm using that z-score again right there, right? 1.96. That's Z. And we know sigma, right? Sigma's 4.11 still got the same dolphins. So now I just gotta throw all that stuff in. So N, to be really honest, I don't know why I wrote it like that. I like doing this better, but you guys can do it either way. 1.96 times 4.11 divided by 0.5, whole thing squared. Or you can square each piece, right? They're the same thing. .96, so like, I don't know, like 196 just about. Maybe a little less, like. It's 196, where did we get that from? 16, is that what that is? 64, 256, so. 256. I don't know, somebody please save me for myself. So you can either do parenthesis 1.96 times 4.11 divided by 0.5, and then put a square on the outside. Or you can do 1.96 squared times 4.11 squared divided by 0.5 squared, because the math don't care.
So that's how big your sample size has to be?
Yep.
Okay.
Now, what's kind of wrong with this?
That's big.
It's
Well,
decimal. You can't
Yeah,
have
I
0.5.
really don't want any of you to go out there and start chopping up little dolphins and saying, I'm sorry, last little dolphin, I just need 0.57 of you. So what we always do is we always round this up to make it a nice whole number of people or dolphins or dogs or whatever the hell, so we're not all chopping things up out there. So I would need a total of 260 dolphins if I want to try to get to within half an inch of the real. And to see how this all jives, the first day you knew, even before the first day, before you ever saw me, before you knew I existed, you knew a bigger sample was better. You just knew that. So here's a bunch of math saying, oh yeah, bigger sample's better. So now you can see what a sample does. It decreases the error that I would get. Crazy. Okay. Is that all so far?
That is A-okay.
Okay.
The fact that I'm not gonna use
I understand. All right. Last thing for today.
You already said that, yeah.
Did I?
We have plenty of time.
Everybody's looking like that's not the right answer.
Actually, Ms. Waller, the clock is off. It's off by like 30 minutes. All right.
Let me see if I can sneak this in here a little bit. So like I told you, we're going to do, the reason that I do 8.3 before we do 8.2, oh, you're going to be really excited, is because, you know how we have the Z-score chart? Doesn't that sound like a great beginning? So in section 8.2, we're going to get a new chart that we're going to use in certain situations. It's sort of related to Z-scores, yes. Okay. So that's one reason why, and 8.3 still uses a Z-score chart. So that's why I disagree with the book's ordering. I'm going to do 8.3 before we do 8.2. So this is all we're going to do with 8.3. 8.3 is all about making confidence intervals for percentages. And this relates to, does anyone, did I ask you this already? Did anyone pay any attention to the polls leading up to the last election?
No.
Did anyone know there were polls done before the, did anyone know what the last election, there's an election for Gavin Newsom to get kicked out, but I'm not talking about that one. I'm talking about last year, right, for the president. Did anyone pay any attention to polls at all? Have you ever seen a poll's results, ever?
Yes.
Right, so
But do I remember
it's
that?
got like, old white dude A, and dude B. Unfortunately, I'm sorry. Someday we're gonna get there, but we're not quite there as a society, I guess. But basically, it's mostly old whites, but, 42% we're gonna vote for that person, and 45% we're gonna vote for that person, but at the bottom of the screen, you would see plus or minus 4%. So do they just go, hey, Jim,
Yeah, what's up, Frank?
how sure are we about, just put plus or minus 4, cover our ass, we don't know. No, this is obviously gonna come from that error part of the equation. Yes, that's where the plus or minus is.
That's the equation that we just did.
Yeah, not quite. It's going to be the equation that we have to modify so it becomes one for percentages. The equation we just made is for sample means. I needed an equation for percentages. So that's the last thing we're going to do is we're going to create that equation and then we're going to get out of here. Okay. Yes, I know that in 2016, thankfully, it was a dudette. Maybe, I don't know how you felt about the dudette. And of course, in 2008, we had an election with somebody who's not an old white dude. That was different, right? But unfortunately, it's mostly old white dudes. Now, so 2020, we had a classic election. So I'm going to start sort of in the same place. Do you remember where we start? I kind of, when I got to the technical part, I started here, right? And what we just did, just to remind you, is we created this equation from that framework, right? As I replaced the mean with the sample mean, which meant I had to change the standard deviation. Yes?
Okay.
Let me see if you guys are cool with this. What is the purpose of this? What is it supposed to try to do?
Find the confidence interval.
That's what it does directly, but what's the purpose of a confidence interval? It wants to catch
The area.
the population mean. So if I write this, the mean is approximated by this interval. Does that make sense? Okay. Alright. So now, watch this. If I have a percentage, so if I'm talking to people and I'm asking them, are you going to vote for this person or not? Isn't that a Npq problem? Am I not going to have a certain number of people I talk to? I'm going to have a probability that they vote for somebody and a probability they don't vote for somebody. They don't vote for somebody. Now, an immediately awesome thing is going to happen. If I have a population mean, does that symbol look the same as the sample mean? Nope. If I have a population percentage, which is the letter P, do you think it's going to look the same if it's a sample percentage? No. So what does a sample percentage look like? P with a hat. Yes, so the P hat is what you don't want to wear. So it's a little party hat, a little party P.
And N is the same, because that's just the number.
Yeah, and it doesn't guarantee a sample size of whatever included. Yeah. So now watch. Remind me, what is the mean for an NPQ problem? N times P. So what is kind of like the sample mean? Would it be N times P hat? You guys get that relationship?
Yeah.
What is the standard deviation for an NPQ problem? NPQ. So what is the standard deviation for this? It would be square root of N P hat Q hat. Okay, now watch. So I'm going to throw all that shit up in here. Same way we did to get this. So I'm going to replace this with N P hat. Is that cool? Because I don't know mu, I know X bar, and I get that by doing N times P hat.
Okay.
Give or take, just like before, because I got to walk them down. It's still going to be making a confidence interval, so it's not going to fundamentally, this picture is going to be the same. But what do I replace this with? I replace that with this. Because that's the standard deviation in this situation. And this catches the real mean. Is that cool? What is this confidence interval going to do? It's going to catch the real mean. So here's the sample mean, give or take z times the sample standard deviation. Is that what I want though? I want an interval for a percentage, correct? I don't want an interval for a mean. I already got that. What do I wish wasn't here? No? The n. If that wasn't there, wouldn't that be an interval for a percentage? Right? Would it be a percentage, give or take? Something?
Okay. So what about the N inside the?
That too.
That's fine. That's not.
No,
okay.
something's gonna have to happen because of algebra.
Not okay. Okay.
So how do I kill n? Don't I just divide by? So now, I I can catch the real population percentage. I can catch it with p hat plus or minus. Now this, we can do something with. Can I just kill those n's?
No.
I had that teacher accent or whatever, teacher inflection there when I said, you know the answer is no when I say it like that. Can we just do, no, Jen. Why not? Because this is half an n, right? You can only do it if the roots are the same.
Okay.
What, square root of what is n? The square root of what is n?
N squared?
Square root of n squared is n, yes?
Yeah.
Why do I have to do that? Because I can't cancel shit unless they have the same root. Remember that from algebra?
Yes.
Maybe? No? Those are dark days? I'm sorry. So what we end up with, okay, see how we can kill one n now? Because they're both in the square root?
You lost me just now. Why
Why?
did you cross out the 2?
Okay. Let me do this.
But wouldn't you just cross out?
Right?
Okay.
And then one n cancels. One n cancels. One n cancels. So how many n's are left down here? One.
Because n squared is just n times n, so
Yeah.
just chop it off.
Yep. So then here is the formula for the confidence interval of a percentage. Holy shit. And I think there is not a card here for you, but if you look on the other side of the sheet, holy shit. So then, yeah, we got some more to talk about. I'll have to explain what the hell that is. Because real quick, I didn't really make a big deal out of this, but it kind of was said, why were we able to do this problem at all? How do I know that? Oh, they do, don't they? Yeah.
Well, and
Did I
that's
have to be
the
told that?
sample is
Yeah,
bigger.
sample size is big enough. So for percentages, there is its own check. So we'll do that next time, don't worry. There's something equivalent to n greater than 30 for percentages that we have to kind of talk about. But I think that's enough for today.
So we should try to do 8.2, because 8.2 doesn't make any sense.
Yeah, you don't even have the right chart to do it at all yet. So.